So let me also connect it here. One second. Okay, so I hope it's visible to. Okay, so this is the seventh class on electromagnetic theory, and in the last class, which happened yesterday, we had been discussing about Faraday's law and how changing magnetic fields can result in electric fields, and changing electric fields can again cause magnetic fields. And we saw how Maxwell brought a modification to the Ampere's law, and finally, what we get out of the Maxwell's equations. And then what we saw is that when you have a wave, you the wave follows. So basically, electromagnetic waves will follow the Helmholtz equation, and those relations are also derivable from the Maxwell's relations, right? So we'll start with electromagnetic waves, and in today's class, what we'll try to focus on is that if you have a wave, and now if the wave moves from one medium to another, how does the medium properties affect the wave transmission, right? So that is what we'll discuss today. So this is just a recap of what we had discussed in the last class. So if you remember, we first said that, so what are waves? Waves are something which has a variation with time and position. So if you consider the Helmholtz equation in 1D, it would look something like this. And here f, which is the wave function, has a temporal periodicity, and it also has a spatial periodicity. And one such example of a wave which would follow the wave equation would be some sinusoidal wave, okay, or some function like this. So here k z, this term shows that this shows the direction of propagation of the wave. So here it's propagating in the positive z direction, and this is called the wave number. And then you have omega, which is the frequency, okay, and delta is some phase. Okay, now to recall, if you have a space where there is no extra charge or no current, that means rho and j is zero. So in such kind of a space, we can see that the Maxwell's equation takes up a form like this. And from here, if you do curl of E, and if you use the identities, we would finally get an expression like this, right? Making use of this uh, property like curl of B. So this gives you a relation, and here, if you put divergence of E going to zero, you would be getting this wave equation. Similarly, for B, you would get a similar equation. So this shows that light is an electromagnetic wave. And if you compare this with the traditional Helmholtz equation form, you would see that the velocity of the wave is given by the speed of light, which is for free space given as 1 by root over epsilon naught mu naught. Okay, 3 into 10 to the power 6. So this was about electromagnetic waves in vacuum moving in in free space. Okay, and there we saw that how do we understand that the electromagnetic waves are transverse? So if you recall and try to use the boundary conditions, you would see that because divergence of E and divergence of B goes to zero, so this shows that the component of the electric or magnetic field in the direction of propagation of your wave should be zero, which means the electromagnetic waves are transverse. And from Faraday's law, we get to this relation which shows how electric and magnetic field amplitudes are related to each other. So if you know the electric field, you can use this relation to find the magnetic field, given you know the direction of propagation of your wave, right? And the frequency. So the similar kinds of formula were used in some of the questions that we discussed in the last class. And we also saw that the energy per unit volume, U for electromagnetic fields, is given by this relation. And from here, so you can see that if you use the relation from the Faraday's law, you'll see that the electric and magnetic fields have equal contributions. This is how the Poynting vector is defined, which shows which points at the direction of the energy flux density. So it's the direction in which the energy travels, and it's in the direction of propagation of the wave, and it is given by E cross B by mu naught, right? So this is something we had discussed in the last class. Now, what we want to discuss now is that suppose if there is an interface which separates two boundaries, right? And if you move from one medium to another, so two mediums are there and there is an interface in between. And if you move from one medium to another, how does the medium properties affect the wave, right? So one can think of it at the first place as some string, okay, with a knot at one point. And now if you try to vibrate the string, you would see that there'll be one part of the wave, this vibration will create a wave in the string, and one part of the wave will be reflected back, while you'll also have a transmitted wave in the on the other side of the knot, right? So that means when you have a incident sinusoidal wave, and when it passes through an interface, one can expect two things. One is some part of the wave will be reflected back, and some part of it will be transmitted, right? So if you write it in terms of the mathematically in terms of a wave function, you write it as something like this. So here, this is your incident wave, right? AI, and this is the reflected wave. So if your wave is coming from z less than 0, then at once it strikes this interface, you'd have a reflection, right? And because of this reflection, you will have this AR e to the power minus k1z term. So minus k1z hints at the fact that now your this part of the wave is propagating in the minus z direction, while the incident wave was propagating in the plus z direction. So it's the reflected wave. And then for z greater than 0, that is on the other side of the interface, you have a transmitted wave. Now, it's important to note that because this is some medium and this is some different medium, that's why the wave vector in z less than 0 is different from the wave vector that we have for z greater than 0. Right? Here it's k1. Also here it's k1 because it's in the same medium, while here it's k2. Now, we have to look at what happens at the interface, right? So in this case, the interface happens at z equal to 0. So mathematically, what we have to check is that at the interface, the wave function should be continuous, right? And the derivative of the wave function should also be continuous. So then your wave function is actually well defined, right? So whenever we have questions like this, if we want to see what are the conditions that the wave has to satisfy in such kind of transmission from one medium to another, we have to use this relations that at the interface, the wave function should be continuous and the derivative of the wave function should also be continuous, right? Now, because these are sinusoidal functions, so one can write it in terms of the complex notation. So because complex notation makes, generally dealing with, like we can write it as e to the power I theta, and there dealing with this becomes easier. So you can easily add a phase to it, and there are formulas. Mathematically, it becomes easier to deal with. In real life, what we actually take into consideration is the real part of this complex notation, which is our sinusoidal or complex or cosine function, depending on the question that we have. So that means, as you can see here, so this is a complex, this is written in, this wave is written in terms of a complex Euler notation, right? So here we write it as e to the power I theta is equal to cos theta plus I sin theta. So that means if you have some sinusoidal or some cosine function, you can write it in real life. If you have to write it, then you have to write it as real part of this quantity, right? So if this is your function, the real part of it is what is your uh, for what you actually see physically, right? And now what we do is we try to apply this boundary conditions. So if you apply this boundary conditions, you'd see you'd get these two relations, right? So this is how these coefficients are related to each other once you apply the continuity relation equations conditions. So if you do that, you would be finally getting this expression which relates how the incident wave amplitude is related to the reflected wave amplitude and the transmitted wave amplitude. So here V1 and V2, these are the velocities of the wave in the two different media. Okay. And as we know, we can also change it in terms of the refractive index of the medium, right? So now, because our this light is a transverse wave, that means if you know the direction of propagation of your wave, there are two perpendicular directions in which your polarization can be. Okay, so suppose your wave is propagating in z direction, that means there are two options for the electric field. Okay, so one is it can be both for the electric field and magnetic field, and each of them will be mutually perpendicular to each other. So if you think of the electric field, that means the electric field has two options. Either it has to be like basically it has to be either a vertical polarization or a horizontal polarization or a combination of the two. So somewhere the plane of the polarization should be perpendicular to the direction of propagation of your wave, right? Now, if your polarization vector is given as n cap, then because it's a transverse wave, that means n dot z cap should go to 0. So for any polarization angle theta, this is how you can define your polarization vector. Okay. So in general, both electric field and magnetic fields will have this kind of, you know, what do I say? So if electric field is along x, then the magnetic field will be along y. If given that the propagation is happening along z, so they should be mutually perpendicular to each other. When we define polarization, we define it in terms of the electric field oscillations. Okay. Now, if you have a electric field which is pointing in the x direction, that means, and if you have a wave propagating along z, that means B is along y. And this is how E and B should be related to each other, which comes also from the Faraday's law, right? So now, suppose if you have a field like this, so it's important to note that n cap dot k cap will go to 0. Okay, this is because your it's a transverse wave. So here, when you write it as kz, it's because the direction of propagation is along z. In general, like in general terms, if the propagation is in any random direction given by r, then your wave expression, like if you want to write electric field or magnetic field, it will have a k dot r term, right? So suppose in any question, if your expression of electric field is given from the terms which include the position coordinates, you can try to find what the wave vector is. So in general, it will have a k dot r term. Okay, so later in the questions, we'll see how from the electric field expression, we can try to find the wave vector. This is just a repetition. So we know this is how in free space the energy per unit volume should look like. This is how the Poynting vector should look like. Okay, and this is the momentum that your wave carries. And it's important that this term here is the radiation pressure, which says that that means light or electromagnetic waves can exert pressure. Okay, and this lies at the heart of optical tweezers and this kind of manipulation with light. Okay, and there has been a lot of research in this direction which makes use of the fact that electromagnetic waves can exert pressure. So this is the expression of the radiation pressure that the light exerts, which is given by 1 by A into rate of change of momentum, okay, which is given actually by intensity by C, okay. And it's important to know that intensity is related to the electric field by this relation, okay. Now, talking about matter. So till now, we were discussing about electromagnetic waves in free space. And now if you have some matter, okay, so then there'll be some modifications that will happen in your Maxwell's equations, and it is pretty straightforward. So in free space, we know that the permittivity of free space is given as epsilon naught, and the permeability is given as mu naught. Now, when you have a different media, that means you have to replace your expressions with the relative permittivity and permeability of your medium. Okay, so that's how these changes come in. And here we can make use of the relation between D and E, which is given as D equal to epsilon E, right? So as you can see here, the only change that is happening is that mu naught and epsilon naught is now replaced by mu and epsilon. So here, because it's in a different media, which has different medium properties, so the velocities now get changed. So in free space, the velocity is given as c. Here it's given as c by n, where n is your refractive index, which is nothing but the ratio of, epsilon mu by epsilon naught mu naught. So if your materials do not differ much in terms of the magnetic properties, then it's basically the ratio of epsilon. Okay. So this is how you define the refractive index. And now this is again the energy expression where you have epsilon and mu coming in. The Poynting vector also changes. So in all these expressions, you are replacing the speed of light in free space, which is c by v, which is the speed of light in that particular medium. And you're replacing epsilon naught by epsilon and mu naught by mu. Okay? And it's important to remember this boundary conditions, because now we will be talking about what happens when we move from one medium to another and what happens at the interface. So there we'll be using this boundary conditions that we had derived from the Maxwell's relations. Okay. So just to recall, if you have some surface with some charge, surface charge, we know that if you consider a Gaussian pillbox like this, then if there is a net free charge on the surface, then d below perpendicular minus d above perpendicular will have a discontinuity, which is given as sigma. If there is no free charge, then this goes to zero. So then your perpendicular components become continuous, right? Because divergence of B is always zero, that means the normal components of B will always be equal below and above the surface. Okay. Again, from the third Maxwell equations, we could get to this expression. So here you can consider a line integral, okay? And there that would result in this relation, which says that the parallel components to the interface are continuous across the boundary. And from the fourth Maxwell's relations, we can get to this expression, which relates how the magnetic field intensity is related to the surface current density, okay? So these relations are what is given here, and we will make use of this when we talk about transmission of waves. So now let us talk about transmission, reflection and transmission at normal incidence. So here we consider, so this is your incident wave, okay, and it's moving in the positive z direction. This is the electric field, this is the magnetic field, and now it travels in the positive z direction and hits the interface. Okay, now once it hits the interface, you would have a reflected wave, right, which would be propagating in the minus z direction, and you will also have a transmitted wave which would be propagating in the plus z direction with the different wave vector k2. And now if you apply the boundary conditions that we initially discussed, so from the third relation and the fourth relation that we had just now discussed, we can get to these two expressions which relate the amplitudes of the incident, reflected, and the transmitted light, okay, with the material properties. So using this, what's interesting is we can get an expression like this, which, so here you can see N1 and N2 are the refractive indices of the different media, like the two mediums, and this is the incident amplitude, this is the reflected amplitude, and this is the transmitted amplitude, right? So from here, now if you want to find the intensity, what you have to do is a square of the amplitude. So R gives the ratio of the reflected intensity to the incident intensity, which is given by this relation here. And this is the ratio of transmitted light intensity. And you can see that R plus T goes to 1, okay, which is what should happen. So a part of the incident light is, the incident energy is either reflected and a part of it is transmitted. And this is how they relate to the refractive indices of the meteor. So now what we got, the expression that we had just derived is for the case where the incidence was normal incidence, right? But now if you have an oblique incidence, okay, so where there is some angle of incidence given as theta I, so then there is a angle of reflection, and then you have an angle of transmittance, okay. So in that case, how do we work out the equations? So the difference that will come in is that now the components along the parallel and the perpendicular directions will change, right? So we have to take the projections of the wave vector in the direction parallel and perpendicular to your interface. And accordingly, you have to use your boundary conditions. Okay, so let us work it out. So here, what we see is that this is the incident monochromatic plane wave. So this is the reflected plane wave. So here you can see that the you'd later see that Ki and Kr would actually be the same because they are in the same media. And then you have a transmitted wave. Okay. Now, because all the three waves have the same frequency, that means your K1 V1 should be equal to Kr Vr equal to Kt V2. Okay. So this gives you the relation about how the wave numbers are related to each other. Okay. Now, this relation should always hold, you know, the the boundary conditions should always hold based on whatever be the position and the time coordinates. So that means so if you just compare the exponents should follow this relation. So because the boundary conditions must hold at on all points in the plane, that means this exponential factors must be equal. So now you then for any particular time, that means your k1 dot r, kr dot r, and kt dot r should be equal. Okay. So this is what you get at the interface. Okay. And now you can write it explicitly in terms of the different components. Okay. So if your k, so if your wave is propagating along z, that means your k can your yeah. So if your wave is propagating along a particular direction, and then if you try to equate the wave number components, that means that based on, like, you can just choose. So suppose you choose x to be 0. So in that case, your k1y, kry, and kty should be equal. And similarly, if you put y to be 0, then this terms, the x components, x parts should go to 0. So now, based on what axis you choose, you can take any of the axes such that one of the components, either x or y, goes to 0. So you have the freedom of choosing your coordinate axes, right? So that gives you the fact that, so it finally leads to the geometric optics rules, which says that the incident, reflected, and the transmitted wave vectors lie in the same plane. Okay. So what we are currently doing is we are seeing that based on the Maxwell's relations, if you try to use the Maxwell's relations in the wave propagation, we finally get to the same geometrical optics laws that we had initially studied. Okay. Similarly, now if you use the concept that, so here K1 x is nothing but the component of K along x, right? Similarly, KR x is the component along x of the reflected wave. So if you take the angles, so if I go back, now you are trying to take the angles along the x. So one will be k1 sine theta 1, this will be kr sine theta r, and this will be kt sine theta t. So that means they should be equal to each other. And because theta 1 and theta r should be, so we know that the angle of incidence should be equal to angle of reflection, and that the same expression is what we derive here, because k1 should be equal to kr because the medium is the same. And now if you compare k1 sine theta 1 with kt sine theta t, you'd finally get the Snell's law. So basically what we have derived till now is the fundamental laws of geometrical optics. Okay. Now, one thing important to note is total internal reflection. So when, for a particular angle of incidence, if your angle of refraction goes to 90, that is called the critical angle. And if your angle of incidence goes beyond the critical angle, all of the light is reflected back. Okay, so that means, so later, I think we will discuss this further, where we'll see that in cases where the incident light is incident at an angle greater than the critical angle, you will see that the transmitted wave is actually a evanescent wave, which gradually, whose amplitude keeps on decreasing. Okay, you would get a imaginary wave number there, and while and that is because the the light is all of the light is actually reflected back. So the transmitted light becomes a uh, exponentially decreasing amplitude wave. Okay. So we'll talk about it in the coming slides. So now here what we do is if you apply the same boundary conditions, so the process remains the same, but here we take into account the components. So we have to be careful about how we choose the components. And so suppose the polarization of the incident wave is parallel to the plane of incidence, which is the XZ plane for this particular question or derivation that we are discussing. So here that means when you write the X components, you have to write it as E01 sine theta 1. Here it will be ER sine theta R, right? And here it will be minus E0T sine theta T. So based on that, similarly, you can see that. So this is coming from the boundary conditions. Just now, because of the oblique angle, your theta I, theta R, and theta T gets involved in the boundary conditions. Okay. So from here, what you would see that again, you'd be able to get a relation like this, which relates the incident wave amplitude with the reflected wave amplitude and the transmitted wave amplitude. So these are called the Fresnel equations. So I'm not going step by step because I think this will already be discussed in the main class. But basically, this is how you get there. Now here, it's important to note that you can see that when alpha is greater than beta, okay, so or so in this case, if alpha is greater than beta, that means they're in the same phase. But if the opposite happens, then there is a 180-degree phase difference that comes in. Okay. So based on what your medium properties are, you can have this kind of phase difference between the incident and the reflected waves. And this is one particular case where, so when alpha is equal to beta, your reflected light. So for the case where the polarization of the incident wave is parallel to the plane of incidence. Okay, so in this case, as you can see, when alpha goes to is equal to beta, your reflected wave is zero. Okay, so this is called the Brewster's angle. So when the incident angle is at the Brewster's angle, which is from this, which is like this is the formula, but at that point, so what happens is you get a polarized light. So your light gets polarized in the reflected regime. So because when you have a parallel like for this polarization, there is no reflected light. So now if you have the incident wave perpendicular to it, you will have a polarized light. So this is what we were discussing, and I think I had seen some questions in this direction where, so this is what is critical angle, right? So when your refracted angle or the transmitted angle goes to 90. Okay. And beyond that, the total light gets reflected. So that means what happens at that point is if in general, if we normally write the wave vector for the transmitted wave, it will have an x component, which is given as sine theta t, and it will have a z component, which is given as cos theta t. Okay. But now, because you are moving from a denser to a rarer medium, and in that case, what is happening is this term is becoming greater than 1. So that means your cos theta t term now becomes imaginary. So that means when you include this wave number in your expression of the wave, you would get an exponentially decaying amplitude. Okay. So suppose if you are asked that, you are moving from a denser medium to a rarer medium, and it is said that how far will the light propagate such that the amplitude gets reduced to this much amount. So that means you have to use this relation where you have to first calculate k, which is the imaginary part of the wave vector, and from there you would get the relation of how far you have to go for a certain decrease or certain drop in the amplitude. Okay, and this is how k is related. So this relation that you see again comes from the initial relations that we discussed, right? So from this relations, we can get to this. Okay, so this is the relation that you have to use where you have the incident angle provided, you have the incident refractive index of the incident medium, the frequency, and this is speed of light. So given these quantities, you can try to find k, and you can try to find how far it has to go for a certain drop, right? So this was one question in the last assignment, which spoke about once the light goes from glass to air, okay, and the incident wavelength is given, and the angle of incidence is given, and said that it has to travel a x naught distance such that the field reduces by a factor of 2, and you are asked to find x naught. So in this kind of questions, what you have to do is you have to use this relation, right? So if you use this relation, you can try to find k, and your wavelength is given. That means you can write it as 2 pi by lambda, and that would be your wave vector. So you would get k from there. Your angle of incidence, that is theta I, is given, okay? And your n1 is given, n2 is given. So now you can use this relation to find k, which is the attenuation coefficient. And from the attenuation coefficient, if you write it as, so then you use this relation, right? So for certain value of z, your ET will go to E naught by 2. And that is the z that you have to find. So this is how you have to do this kind of, answer this kind of questions. Okay. Now, when we move to electromagnetic waves in conductors, so now an additional term comes in. So when you have conductors, you have free charges. That means there is a conductivity which you have to consider. So this conductivity results in a free volume current density, and that comes in this expression. So you have an additional term here, which comes because of this J free charge term, right? And we know that from the continuity relation, this is how J is related to the free charge density. And from here, an interesting point comes in. So you can see that the free charge density dissipates with a characteristic time scale given as epsilon by sigma. So what is this time scale? So if you remember, when you have a conductor, we said that if you put some charge on a conductor, the charge goes and gets distributed on the surface. So that means the volume charge gradually dissipates. And this is the time scale of how fast this dissipation happens. So if you have a very good conductor, in that case, your sigma will be infinite. So that means your tau will be 0. So the charge will immediately go to the surface. Okay. While in general, you don't like in general, sigma is a finite quantity. So there you'll have a finite time which it takes for any charge that is there in the bulk to go and distribute on the surface. Okay. So this is the relation that the volume charge has in the transient times. But now we are not interested in the transient behavior, and we would concentrate on the time scales where this equilibration has already happened. So now all the charges are on the surface. So if you consider rho f to be 0, this is how your Maxwell's relations will get modified. Okay, and because of this extra mu sigma e term, you would see that your wave equations will also have this additional terms here. Now, when you solve for this wave equations, you would see that now your wave number will be a complex quantity with a imaginary part. Okay, so that means now your wave number can be written in terms of a real part and an imaginary part. Now, this real part is actually the related to the velocity of your motion, velocity of the wave, and so you if you want to find the velocity of your wave, you have to use the real part, while the imaginary part talks about the attenuation of the wave. Okay, so how much of the wave gets attenuated as it moves through the conductor. Okay, and in cases where you have a good conductor, so there you would see that this imaginary term would have an expression like this. So this is a very useful expression which relates the conductivity, the material permeability, okay, and the frequency of your wave to the attenuation constant. Okay, so this is how this is related, and it's very useful. And here 1 by k, okay, that would give you the amount of distance it takes for a factor of 1 by e decrease, and that is called the skin depth. So in general, there could be direct questions which ask you about skin depth given the material properties, and then this is how you have to use this relation. Okay. Okay. So now again, because your k is a complex quantity, that means you can write it as some modulus into e to the power I phi, where phi is some phase. Okay. How do you find the phase? The phase would be given as tan inverse imaginary part by the real part, right? And root over of k square plus chi square would actually give you the modulus. So that means now if you write the expression of the electric field and the magnetic field, and if you use the Maxwell's, the Faraday's law, then you know that this is how the magnetic field is related to the electric field. So it's important to note that now the magnetic field is no longer in phase with the electric field. You have an additional pi phase which comes in. So magnetic field lags behind the electric field by this phase, which is phi. Okay. And the phi is given by this expression here. Okay. And how are the amplitudes related? So they are related by this relation here. So again, it is dependent on the conductivity of the medium. So that means for a conductor, if the electric field is given, now you can write the magnetic field again using the Faraday's law, and this is how they will be related. And there you have this e to the power minus kz term, right? So it's a exponentially decreasing amplitude that you get. Okay. So in terms of any medium, there is one important parameter, which is the wave impedance, which is given as the ratio of the electric field intensity to the magnetic field intensity. So for a conductor, you would see that you would get an expression like this. So now if sigma is 0, which is for any other media, which is not a conductor, so there you would get the wave impedance as root over mu by epsilon, right? So in free space, the wave impedance will be root over mu naught by epsilon naught, which is a fixed value, right? And that value is something which one should remember, and that is around 377 ohm, right? So its unit is in ohms. It's a kind of a resistance that the wave feels as it propagates in the medium. Okay, and this term here, so chi by k, so this term here is called the loss tangent because it talks about, so as you can see here, this is related to the attenuation that the wave has. So there can be direct questions which ask you about what should be the loss tangent. So that means, so if you use the initial expressions, you know what is k and what is chi. So from here you can see that sigma by epsilon omega is actually the loss tangent. Okay. So now, given this relation, this was one question from the last assignment, which said that in a given medium, your mu r is 1 and epsilon r is 1.3. So these are the relative permeability and relative permittivity. So what is the wave impedance for this medium, right? So if you use this relation, you have to be careful. So here it's mu and epsilon. So what is mu? Mu is equal to mu r into mu naught. Okay, and epsilon is equal to epsilon r into epsilon naught. So that means this, how do you find this value? This should be nothing but root over of 1 by 1.3 into the wave impedance in free space, right? So we said that the wave impedance in free space is around 377 micron. So that means the wave impedance for this given medium should be something like root over of 1 by 1.3 into 377, which would be something close to some 330 ohms. Okay. Okay. So now, based on what we had just discussed, let us try to solve some questions. So here, what this question is telling us is that you have a plane electromagnetic wave and it is propagating in a lossless dielectric and the electric field is given. Now, the question asks that what is the dielectric constant of the medium and what is A? Right? We have to find epsilon r and A. So the first thing is we have to see what is the information that is already provided in the question. So here you can see that the electric field is given. And here, now if you look closely, so we know that generally the electric field has a e to the power I k dot r minus omega t kind of form, right? So the term with the time here should give us an expression for the frequency, while the term with the position coordinates should give us the wave number, right? So that is what we would try to do. So here, if you write clearly, we would see that. So if you compare with t to the power I k dot r minus omega t, we know that the wave vector should be given as k naught into x cap plus root 3 z cap, right? So this is your k dot r term, and omega should be given as k naught into c. So now that you know the wave vector, you know the frequency, you know the electric field. So now you can also try to find the magnetic field if the question asks, right? Now the question here, what it is asking is the dielectric constant of the medium. Okay. So how do we find the dielectric constant? So one important point is that dielectric constant is related to the speed of the wave, right? So in vacuum, we know that the speed is c. In any other medium, the speed would be given as c by n, right? Where n is your refractive index or dielectric. So basically root over of that. So that means you have to find the velocity of the wave. Now, how do you find the velocity? Velocity is given as omega by k. So now you know what is omega, you know what is k. So that gives you the velocity in this given dielectric. So you know that the velocity has got reduced to half. That means your refractive index should be equal to 2, right? So if the refractive index is 2, now you can use the relation to find your dielectric constant, which is twice that, that is equal to 4. So this is how you find the dielectric constant. Now the next question is, what is A? So how do we find A? So in this, for this part of the question, we have to see what are the additional information that this question has. So in electromagnetic waves, we know that the wave is a transverse wave. That means k dot n cap should, or the direction of your electric field should be perpendicular to the direction of propagation, right? So that means k, which is given by this expression here, dot n cap, which is given by the expression here. So that means that the dot product should go to 0. So using this relation, you can try to find what the constant should be. Okay. So this is how you make use of the information that is provided to you. Okay. Is this clear? Okay. I think so. Okay. Now this is another question which says that consider an electromagnetic wave, okay, between two homogeneous dielectric media with the dielectric constants given as epsilon 1 and epsilon 2. Now, assuming epsilon 2 is greater than epsilon 1 and there is no charge on the surface, how are the electric field and the displacement vectors related in the two media? Okay, so what is the inequality that they satisfy? So how do we answer this question? So here first we have to think is what is the boundary condition that generally gets satisfied. So you have to be careful that here it says that there is no charge on the surface, right? So if there is no charge on the surface, let us go back and see how the expression, how the boundary conditions look like, right? So when there is no charge on the interface, that means this is how the boundary conditions look like. Okay, epsilon 1 E1, which is actually your D1, should be equal to epsilon 2 E2, which is D2. Okay, so this is what happens at the interface. Now the question asks what happens in the medium, right? So that means now you have to understand that. So we have understood what happens at the interface. Now you have to be careful about what happens in the two media in the bulk. Okay. So there, as you can understand that because D is given as epsilon into E, that means if the dielectric constant is more, the displacement vector should be more, right? So that means if epsilon 2 is greater than epsilon 1, your D2 should be greater than D1. Now, if we go back to the understanding of what happens in a dielectric, and from where this concept of displacement vector comes in, we would remember that there what happened is when you have a dielectric and if you have some incident electric field, there would be a polarization, right? And the polarization would be such that the induced field will be in a direction opposite to what is the incident initial field. In a conductor, they cancel each other and so it becomes 0, while in a dielectric, they do not cancel, but it reduces. So that means more the dielectric constant will be, more will be the less will be the net field that will be there, because more will be this cancellation due to the polarization. Okay, so that means here D2 will be greater than D1, while E2 should be less than E1. Okay, so answer would be given by this. So this what we discussed was a very, it's a theoretical question, more of understanding, not a numerical as such. Okay. So now here it says that you have a electromagnetically shielded room where the frequency is given. Okay. And it says that the intensity of the external radiation penetrates this room, which is only 1% of the incident radiation. And your sigma is also given. The conductivity of the shielding material is given. You have to find what the minimum thickness should be. So that means here it is talking about what we discussed in a conductor. Okay. And we saw that there's a skin depth. Okay. So here we'll make use of those expressions. So it says that the intensity gets only a small part of the intensity gets transmitted. So that means there is dissipation of the intensity. And we know that if the electric field goes as e to the power minus kz, then the intensity should go as square of it. So that means you should have a e to the power minus 2 kz term. So from here, you know that this is how z, which is the distance that one has to travel. So that would also be equal to the thickness that is required. So this z is related to the attenuation constant and the ratio of the intensities by this relation. Okay. So now the question says that I naught by I should be 100 because only 1% of the incident radiation get penetrates. Okay. And this is how the attenuation constant, this the expression is related to the conductivity, the mu, that is the permeability of the medium, and the frequency. So frequency is given. So you can consider mu to be 4 pi into 10 to the power minus 7. And you know what is sigma. So this is your sigma. So now if you put these expressions, you'd get an expression for K. And once you find K, you can use this relation to find Z. Okay. So this is how you find it. So this gives you the value of the minimum thickness that should be required such that only 1% of the radiation penetrates. Okay. So this is how this formula of skin depth and attenuations become useful in real life situations. So when you are trying to make a room or make some something which you want for shielding, so there you have to use this kind of relations to see what the effective thickness should be. So this is how it becomes useful in the physical world. Okay. Now, this is another question which is very straightforward. So it says that you have a plane electromagnetic wave which is normally incident on the surface.
Excuse me, ma'am.
Once it is incident, it is partially reflected and partially transmitted. And it says that in the reflected regime, that is in the region from where the light had initially been incident, so there standing waves form. Okay, so standing waves form in front of the interface such that the ratio of the electric field amplitude at the maxima and the minima is fine. So the question is, what is the ratio of the reflected intensity to the incident intensity? So how do we answer this question? So here you have to consider that, so you have some interface and there is a wave which is, so what it means is that if you have some interface, okay, so you will have a wave which is traveling in this direction and there will also be a wave which will be reflected back, right? It is said that the ratio of the electric field amplitude at the maxima and minima is 5. Now, when will be a maxima? That means when the amplitudes of both these waves, if they match with each other, if they match in phase, then it would be a maxima, right? So the maxima would be given as the sum of the amplitudes of both these waves, while the minima will be when they are canceling each other. So the minima will be given as the difference between these two amplitudes, right? So basically what it is telling us is that E incident plus E reflected by E incident minus E reflected is given as 5. So now that you know this, the question is asking you to find the reflected intensity to incident intensity. So now you know how to do it, right? So we'll use the general relations of ratio and proportions, and we can try to find the ratio of the reflected amplitude to the incident amplitude. And the square of this will give you the intensity. So now you know what the answer should be. Okay.
Excuse me,
So
ma'am.
this is not just true for light or any electromagnetic wave. This would be true for any wave. When you have standing waves being formed, this is how you would try to get the maxima and the minima.
You
Okay.
post your questions in comment, sir.
Okay. Now, this is another
Excuse me,
question
ma'am.
which
Hello.
says that a plane electromagnetic wave is traveling along positive z direction. The maximum electric field along the x direction is given. So E naught is provided to you. Okay. And the direction of travel, that is the propagation direction, is along z. That is also provided. The question says the approximate maximum values of power per unit area. That means intensity. You have to find intensity, right? And you have to find the magnetic induction. So given is the direction of K and the electric field. You have to find intensity and magnetic field induction. Okay. So how do we do it? So for the first part, if you recall, there was a relation between electric fields and intensities, right? So do you remember what the relation is? So this relations would be very useful in in day-to-day lives, because in daily lives when we maybe characterize a source, we characterize it in terms of the intensity, right? So how intensity is related to the electric field, do you remember?
Excuse me, ma'am.
By 2, the ratio 1 by 2 velocity into E.
Okay,
Hello.
so let's see.
Hello.
So the first relation is
The
that
recorded
intensity is related
record
to
video.
the electric field by this relation. This is something which we discussed in the last few slides. So if electric field
Yep.
is given, you can use this relation to find
I
the
think
intensity. So
so.
that would give you the first part of your answer. Okay, and there will be something like this. Okay. Now, what happens in the second part? Now, how do you find the magnetic induction? Right? Now, magnetic induction, again, here we'll use the relation of your
Hello.
Faraday's law, which says how the
Hello.
magnetic field amplitude is related to the electric field amplitude. Okay. And this would give you the magnetic field. Okay. So that's how you can use these relations to find the intensities and magnetic fields given the electric fields or the K vectors. Now,
Excuse me,
this is
ma'am.
another question which says
Post your
that
question in chat window, sir.
suppose there is a YZ plane,
In chat
okay, and it
window.
forms a
If
chargeless boundary
uh,
between two media with the permittivity is given, and epsilon left is to epsilon right is given as 1:2. If the uniform electric current on the left is given, you have to find the electric field on the right. So this is a typical question of using boundary conditions, right? So it's something like this, right? So you have two media here, medium 1 and medium 2. You know the ratio of the dielectric constants of the two media, okay? And the electric field in one media is given. You have to find the electric field in this media, right? So that is the question that is being asked. So here you have to make use of your boundary conditions, right? So it's important to note. So whenever you have a boundary, try to see what is there at the boundary. So it's a chargeless boundary. That means sigma is 0. So again, that means you would have to use the boundary conditions which says that epsilon 1 E1 should be equal to epsilon 2 E2, right? So that is this relations. If I go back, so whenever there is no charge, so this is the, one second. So this relation, right? So we'll again go back to this relation. Because we are talking about electric fields, these are the two boundary conditions that we have to think about. So one is the normal components and another is the parallel components. Okay. And you can see the normal component has this dependence on the dielectric constants. Okay. So now let us go back and see how these relations can be used to find the electric field on the right. Okay. So here, one second. Yeah. So here that means these are the two relations that we have to use. So now if you look at the, where is my pointer? So if you look at what it is saying, that your interface is in the YZ plane. That means the Y and the Z components are the parallel components, right? While the X component is the normal component. So that means epsilon 1 E1 should be equal to like E1, that is X. So for this question, this condition should hold for the X, while this too should hold for Y and Z, right? So now that means your for the electric field on the right, the Y and the Z components should be same. So that means if we compare, it should be one of the two options, right? Any of the two options based on the first condition, which says that the parallel components should be equal. That means Y and Z. So parallel means parallel to the interface. The interface is the YZ plane. So that means Y and the Z component should be equal to what is there on the left, right? So this means this any of the two. Now let us use the first condition, which says that epsilon1 E1x should be equal to epsilon2 E2x. And because there is a ratio of, you can see 1:2, this is the ratio of the dielectric constants. That means epsilon1, that is 1 into E left, should be equal to 2 into E right. Right? So that means 1 into C should be equal to 2 into E left, E right X, right? So that means E right X should be given as C by 2. That means the answer for this case should be equal to C, right? So this is how you try to find the expression for the uh, electric fields. Okay, so this is how you use the boundary conditions. Okay. Now again here, you see that the electric field is given and the magnetic field is given. Okay, and you see that they are exponentially decaying. That means they are in a it's for a conductor. Okay, and you see that it's in a charge-free region for Z greater than 0. So what is the average energy flow in the X direction? So X is the direction of propagation of your wave. So that means now, because you're talking about average energy flow, you have to try to find the Poynting vector. Okay, so basically you have to do E cross B by mu naught. If it was in a medium with some given permeability, then this would be replaced by mu. Okay, so this is pretty straightforward. You can try to find the cross product, and this would give you the net energy flow. Okay. Now, this is another question which says that the electric field of a plane wave in a conducting medium is given. Okay. Omega is the angular frequency, A is some constant, which is a positive constant. You have to find the phase difference between B and E. So now we have to again remind ourselves that in a conducting medium, we saw that we had this phi, right? And the phi was related to so it was tan inverse of chi by k, which is the ratio of the imaginary to real parts of the wave number, wave vector, right? So that means now here you have to try to find the real and the imaginary parts of the wave vector. So how do we do that? So first is, let us look at the expression of the electric field. Okay. And this is the expression of the magnetic field. And this should be your phi. So if you compare, that means, see here, you would have a time part and you would have a position dependent part. So the position from here, you can see that if you compare this expression with what you already have here, that means your chi should be given as 1 by 3a, right? So this is just what you are, sorry, I just messed it up. Okay, so first is you compare this part of, so this part, sorry, so this part gives you the real part of your wave vector, right, which is k, and that is nothing but 1 by root 3a. Okay, so this is your k, which is the real part. And this part here gives you the imaginary part, which is the attenuation constant, right? So that is the imaginary part of your k. So that is given as 1 by 3a. So that means comparing how fast your amplitude is decaying will give you the attenuation constant, and this part will give you the the real part of the k. So now you know the real and the imaginary part. So now you can use it to find phi. That is what you have to find. Okay, so if you do that, you would get that the phi is 30 degree. So, and we know that the magnetic field lags the electric field. So in this case, the answer would be B. Okay. Yeah, so that was it about today's class. Do you have any question regarding what we discussed?
Am I audible?
I think you're muted. I'm not able to. Okay, so if you guys don't have any question, let's call it a day. Do get back to me if you have any questions. Okay. Thank you. Okay, so I'll consider that you don't have any doubts.
Hello. Hello.
Thank you.
Hello, excuse me, ma'am.